Previously, we learned how to find the derivative of a function by using the limit definition of the derivative. So I want to begin by taking a review of some of the functions that we have found the derivatives for. And specifically, I want to look at power functions. So let's begin by looking at the power function x squared. Now previously in our notes, we found the derivative of this power function x squared. So let's review what that derivative looks like. Using the limit definition, we first began by finding the difference quotient. So finding f of x plus h minus f of x all divided by h. We find that difference quotient, and then we simplify it. And when we simplify that, we get 2x plus h. Next, we find the limit as h approaches 0, and that limit will give us the derivative f prime of x. When we take that limit of our difference quotient 2x plus h, the h goes to 0, and our limit becomes 2x. So what we found was that the derivative f prime of x of this power function x squared turned out to be 2x. So here in my table, I'm going to write f prime of x of the power function x squared to be 2x. And for now, I'm going to write the exponent of 1, and you'll see why later. We also looked at the power function x cubed. And in your practice problems, you found that the derivative of x cubed turned out to be 3x squared. We also looked at the power function 1 over x. And it might help to write this as x to the negative 1 so that you see it as a power function. It's a power function with the exponent of negative 1. So now let's review what the derivative of the power function x to the negative 1 looks like. When we found that derivative using the limit definition, what we did was we first calculated the difference quotient, so plugging x plus h into the function, and then subtracting off f of x, and then dividing by h. We had to find a common denominator to simplify that numerator. And then once we got done simplifying, we found that the difference quotient was a negative 1 over x times x plus h. Next, we have to find the limit as h goes to 0 to get our derivative f prime of x. Taking that limit of the simplified difference quotient, our h, as we think about h approaching 0, our limit then becomes a negative 1 over x squared. So that is our derivative for the power function x to the negative 1. The derivative is a negative 1 divided by x squared. So next I'm going to fill that derivative into this table. Negative 1 over x squared is our derivative of the power function. And I'm going to rewrite this as a negative 1 x to the negative 2. Now let's observe and see if we can find a pattern that exists in these power functions and their derivatives. What we notice here is that to find the derivative of a power function, we can do so by bringing the exponent to the front of the variable as a coefficient and then reduce the exponent by 1. So take a look in the first power function x squared. The derivative turns out to be, we can find this by moving the exponent down in front of the x and writing it as a coefficient, 2. And then we take that exponent and then we subtract 1 from the exponent to give us 1. Same thing with the power function x cubed. We take that exponent, bring it out in front of the variable, making it a coefficient, and then we subtract 1 from the exponent to give us a 2. Same thing with x to the negative 1. Bring that exponent out in front and make it a coefficient. Here's the negative 1 coefficient in the derivative. And then we subtract 1 from the exponent. So this negative 1 now becomes a negative 2. So now we've identified a pattern that is happening with the power functions and their derivatives. This pattern we have identified summarizes the theorem, the power rule. The power rule tells us that to find the derivative of a power function x to the k, the derivative is found by bringing the exponent k out in front of the x and making it a coefficient, and then subtracting 1 from the exponent, and that gives us the derivative. So now that we know about the power rule, we can use the power rule to find the derivative of power functions instead of having to use the limit definition of a derivative. So this makes things a little bit easier for us. So in this first problem here, we're asked to find the derivative of the power function x to the ninth. So we're taking dy dx of x to the ninth. So using our power rule, we find the derivative by bringing the exponent out in front and making it a coefficient. And then on the exponent, we're going to subtract 1 from the exponent. So our exponent becomes 9 minus 1. So now we can simplify this by writing 9x to the 8 exponent. And that is our derivative. For part B, we're finding the derivative of the function negative 5x. So here what we're going to be using is the fact that the derivative of a constant times a function, f of x, is equal to the constant times the derivative of the function. So we can kind of just pull that constant away from the function and take the derivative of the function and carry that constant along with us. In this case, our constant is a negative 5, and our function here is x. Or if we think of it as a power function, it's x to the first power. So our derivative of a negative 5x, we can pull that constant out front and think about taking the derivative of x. Or if you like, you can think of that as x to the first power. Now carrying the constant along with us, now we're taking the derivative of x to the first power. Using the power rule means we bring the 1 out in front, and then we subtract 1 from the exponent. So simplifying this, we have a negative 5x to the 0 power, which just becomes a negative 5, since x to the 0 is 1. So the derivative of the function negative 5x is a negative 5. One thing I'd like to point out here is if you notice, the derivative of x, the derivative of the power function x to the first power, it turns out to just be 1. We found x to the 0. So keep in mind the derivative of x is always going to be 1. And then for part C, we're finding the derivative of the function 10. 10 is a constant function. And as we saw in our notes, we learned that the derivative of a constant function is just 0. So the derivative of the constant function 10 is just 0. Next, in part D, we're again using the power rule and the fact that a constant times a function, that derivative is the constant times the derivative of the function. So our derivative of 6x to the negative 2, we carry that constant along with us, and then we take the derivative of the power function. So to take the derivative of the power function, we bring the exponent out in front, and then we subtract 1 from the exponent. Simplifying, we have a negative 12x to the negative 5. Or if you prefer, and you want to get rid of that negative exponent, we can write this as negative 12 over x to the 5th. For part E, we're taking the derivative of x cubed plus 2x squared. Notice here we have a sum of two power functions. To take the derivative of a sum of two functions, we find that derivative by taking the sum of the derivatives. Same is true for differences. The derivative of a difference is the difference of the derivatives. So let's find the derivative of x cubed plus 2x squared. We can break this up and take the derivative of x cubed and then plus the derivative of 2x squared. The derivative of x cubed, bring the exponent out in front and make it a coefficient, and then we subtract 1 from the exponent to make it a 2, using the power rule. Moving on, take the derivative of 2x squared. Well, the constant, we can pull that out front and carry that along with us. Next, we bring the exponent out in front using the power rule, and then subtract 1 from the exponent. So simplify this, we have 3x squared plus 4x, and that is our derivative of x cubed plus 2x squared. So here we were using the sum difference rule and also the power rule. In this next one, let's find the derivative of 6 times the square root of x. And it might help if we rewrite this as 6x to the 1/2 power. Now we can view it as a power function. So now to find the derivative of 6x to the 1/2 power, using the power rule, we bring the 1/2 out in front, and keep in mind the constant 6 out front just stays there. We carry that along with us, bringing the exponent out in front, and then we're going to subtract 1 from the exponent. So simplifying, we have 3 as our coefficient, and then subtracting 1 from 1/2 leaves us with a negative 1/2 exponent. If we like, we can get rid of that negative exponent by moving it to the denominator. So we have x to the 1/2 power. Or we could write this as 3 over square root of x, and that is our derivative. For part G, we're taking the derivative of 6x over 7. And if you like, we can think of this as, kind of rewrite it as 6 over 7 times x. So to find the derivative dy dx of 6 over 7 times x, keep in mind the constant, we can kind of pull that out front. And now we're taking the derivative of x. And as you might recall, the derivative of x is just 1. So our derivative is 6 over 7. Now, to remind you, why is the derivative of x 1? Well, we can think of there being an exponent of 1 there. So bringing the exponent out in front and then subtracting 1 from the exponent, we're left with 1x to the 0, which is 1. So that's why the derivative of x is 1.